Hi, thank you all for coming. My name is Nisha Talagala. I'm a fellow at SanDisk. I joined SanDisk through the Fusion IO acquisition. We'll be talking today about various application acceleration solutions that SanDisk and Fusion IO have jointly been developing for a while now. Joining me is Dan Bagent, who's going to introduce himself.
I'm Dan. I work for what we call the Global Technology Ecosystem Group at SanDisk. So I help do the business side of the technologies that Nisha's team builds. For those of you who aren't familiar, SanDisk is well known in the consumer space. We've been doing thumb drives and micro SD cards in your cameras and your phones. We're also embedded in most of the iPhones and Google phones of the world. But they've invested heavily in purchasing several companies that give them a foothold in enterprise storage. Fusion IO is kind of the capstone acquisition that they made last year. So we have a full suite of SAS and SATA drives as well as PCIe flash storage technologies. And we have a whole division that's focused on doing high-performance shared storage targets. We have a product called the Ion Accelerator, which is a high-performance all-flash appliance. And we just introduced something called InfiniFlash, which is a high-capacity, half a petabyte in 3U storage custom flash device. So the hardware side is well understood by the market. What Nisha's team works on are software optimizations that ride on top of the hardware, take advantage of Flash's unique capabilities for managing data. And what I do is help manage the partnerships that get ISVs and software infrastructure ecosystems working with that software platform on Flash hardware to really accelerate enterprise workloads. So what Nisha's going to get into is the details behind the software stack that we're building to complement our hardware. And of course, we want to make this interactive. Feel free to ask questions. That makes it all that much more valuable for both of us.
Don't worry, we will.
I'm sure you will.
Great, so let's get started. So we'll pass through this one. So just a kind of a very quick intro to Flash. Dan did a good description of this, sharing how the, all the different varieties of products that SanDisk builds, which range everywhere from, small USB-style devices to full-blown arrays. Within the enterprise section, which is what the bulk of this talk is going to be about, really we are talking about, drives that are either SAS, SATA, PCIe drives, and then ranging, up to the arrays themselves, the Ion and the InfiniFlash devices. For the flash that is in these kinds of contexts, today we are talking about media that is, typically hundreds of gigabytes to single-digit terabytes, heading close to the double digits of terabyte capacities. We're talking about, media that is, basically primarily, multi-layer cell kind of technologies, heading into, technologies like X3 and, higher density, lower cost type of media, but pretty much all flash. Hundreds of thousands to millions of IOPS in performance and bandwidth. Tomorrow or in the future, there are technologies that are being developed that are, intended to follow and complement Flash, and there's a wide variety of these, phase change memories, memristors, resistive RAMs, and things like that. Those are expected to have another order of magnitude of performance, but they are still, very much in development. And there are some things in the middle, which we'll talk about later in the talk, that are sort of bridging the gap between these two things.
And just to point out quickly, the way this really ought to be better structured is you sort of see the disk replacement products across the top, the SAS and SATA products. In the middle, we actually have something called the UltraDIMM, which is a storage device that rides in the DIMM slot for kind of the lowest latency you can get for flash storage, along with our PCI portfolio. And then on the bottom there are the two shared devices, shared storage devices I was talking about that are storage appliances based on.
Living up to my rude reputation, are you shipping UltraDIMMs again?
Yes. The litigation has mostly settled itself out.
Yes.
So we were not a party to that litigation, by the way. We were just a victim.
A victim of litigation.
I have recommended several times that you should have just bought NetList and ended the whole thing.
Did you?
It was change. It was change. You could have found
somebody who could decide that.
They will take the funds.
You're flight raise your hand. Go ahead.
Yeah. So you said those disk replacements on the one below. Do you call those array replacements, or are these building blocks that OEMs take to do things?
More the latter. So the term array, I think, is overloaded, so we try to avoid it. They're really appliances. The focus is on high-performance storage targets as opposed to full-featured flash arrays.
Yeah. So the disk replacement versus, performance isn't necessarily, devices versus kind of systems. There are some flash products that are targeted towards, very, very low cost per gigabyte, very, very high capacity points, and those are intended to replace disks. There are others that are targeted towards many millions of IOPS, and those are really intended to be more part of the DRAM flash kind of memory subsystem rather than the disk replacement.
I'm assuming your passes all get you into the expo floor. If you go by the SanDisk booth, there's an InfiniFlash box there. If you like the touchy-feely, you can pull it out, look at the cards, and play with it. But again, its focus is high capacity, highly dense flash storage.
I know you guys want to touch storage. This is your big opportunity.
Yeah, unfortunately, the only storage I have here is my USBs.
Well, the only thing I would love to know from the networking side, like high-end accelerated storage array, how many gigabits per second does it push out?
So,
This is from a networking guy.
yeah, so I think, Flash in general, you can get, several gigabytes to, low tens gigabytes a second of throughput, if you aggregate devices. The ion array, which is the, I use the word array, sorry. The ion system actually, keeps up with a lot, so if you're using a network like an RDMA connect and so forth, you can get, 6-7 gigabytes per second out of that.
The actual specifications. The ion in particular is designed for very high bandwidth throughput. Don't quote me because I don't have this memorized, but I believe it's a 40 gigabit networking throughput on the back end. InfiniFlash is not quite as network optimized because it's more of a high capacity, sort of large footprint storage.
Not quite so network optimized is a bit of an understatement. It's hard to call SAS a network.
This is not SAS. InfiniFlash, well, actually, you're right. It's using the SAS protocol. You're right.
That gives you kind of a feel for, what the hardware kind of products look like. What we're going to be talking about in this talk, in the first half of the talk, will be about various things that we have demoed over the years and now released over the last several years, and we'll be talking a bit about the software that's been released and what it's for and things like that. The second half is really more about memory technologies and where we're going there. So on the first half, really, the focus is, going back to the point that you made about, how much, performance can you get out of these. The flash devices are extremely capable of delivering, a massive amount of performance. What we've found, and this is true in the system world as well as in the server world, is that after you get past a certain speed of a device or a certain number of devices you gang together, the software is what gets in the way of your performance. And if your software is trying to, send your flash performance to your app, that's one bottleneck. If your software is trying to push your flash data over the network, that's a separate kind of thing. But the problem is the same. There's usually a piece of software in there, and it's providing some service, but it is also typically getting in the way of the performance. And so this has been known for a while. Many applications even today were written for HDDs, and there's a lot of HDD-related optimizations that went in. And so, a lot of people have worked, for many years on how to tune these applications for, better performance with Flash. Think of Flash as a disk drive just 100 times faster. And then now what do you do, kind of thing. But the phase of flash optimization that we focus on right now is really recognizing that it's not just faster than disk, it's also inherently different from disk. And this actually becomes more important because flash, as it moves forward, is becoming more and more different from disk. So it is not moving towards being like disk, it's moving towards being, for example, flash, when you move into 3-bit per cell technologies and things like that, the endurance goes down. They are focused on high density, lower cost devices. And so the characteristics that, make the read-write difference and so forth become more extreme in the newer generations of flash than, they were previously. So I'm not going to go over all of these details here, but what these show is that there's lots of different areas where even if you're accessing the stuff as a disk drive, it just behaves differently. It has different characteristics, it wears out.
You're underselling the power and cooling.
Yes. Even lower.
Yeah, certain parts of the world, you've got no choice.
Yeah.
But,
Even lower than what? Yeah.
Well,
Even lower than SanDisk, right? Significant lower.
Yes.
And you might just well say even faster, I mean, yes. How about order of magnitude lower?
Yes, and this is actually a very important thing, which is if you can recognize that it's flash and it can be, optimized uniquely, the level of improvement you can get in power, in cooling, and I have some charts on that, and the lifetime and the cost is just another order of magnitude.
Howard loves short-striking disks, I know, so.
I came from the disk world before I started working on flash. I have a lot of sympathy.
But I think, so the other thing I don't want to underemphasize. The other thing I don't want to underemphasize is the comment that Nisha made, twofold. One is, it's one thing to replace disk with flash, which gives you a really fast disk, and that doesn't take full advantage of flash and its ultimate capability. That's one. And the other thing is the impact it has on data center architectures. Because software that used to only care about getting to the I/O path as fast as it can and then it waits, now suddenly becomes the bottleneck in application architectures. And so what we're seeing in the data centers that adopt flash across the board is first they get great performance and they're very happy with it, then they start reaching new limitations, and the limitations are all in software. And that's where Nisha's academic studies are all focused.
This is the single true thing about IT. You can't eliminate the bottleneck, you can just shift it.
Exactly.
Yes.
And it's shifting closer and closer to the CPU and closer to the actual application instructions. And now software developers are going to have to put their hats back on and figure out how to really optimize software going forward.
Like in networking, the application is the problem.
Software defined.
It's always the network or the developers from this side of the table. From that side of the table, it's always the storage or the developer.
Let's just make peace here, Howard, and just say it's the DBAs. Can we all agree to that?
Yeah, that's it.
Yeah.
Till data field day,
Yeah.
it's the DBA.
Sorry, guys.
Good. Very good. It's interesting because I was reminded, like the very first million IOPS demo that I saw out of an SSD, and I won't say where it came from. The little known fact about that was that the software using to just get those million IOPS consumed about 7/8 of the CPU of the machine. So there was a million IOPS, but there was no app running that could use them. There was no room for it to run. There was no CPU left for it. And then, people have been working on Linux now for a long time, and one thing that Fusion IO did about a year or so ago is they pushed the Linux block IO stack to 15 million IOPS, which it had never ever hit before. And the interesting thing about it is that the first 3 or 4 million was done in about 4 cores or so. The remaining 10 million took 80 cores. I'm not sure where they got the cores, but that's where it took. So clearly says, this is not a solved problem.
Probably on Amazon. They probably got all the cores in Amazon. You spin it up, doesn't cost that much.
So now this, one of the things that we've been talking about it right now, but let me put it into sort of phases, which is we're going through really a life cycle or a multiple phases of application optimization. The first one is the one we've been talking about, which is it looks like a disk. Let's put it in, recognize that it's a fast disk, and do whatever it takes. First, you're very happy. Then you try to become happier, and you do what you can to get the fast disk as used as possible. Then you recognize that it's actually not just fast, it's actually not a disk at all. And it reads and writes differently, it has kind of a wear problem, its performance changes over time. If you try to buy the cheaper ones, they seem to have less endurance, and so on and so forth. And so this is what we call flash beyond disk, which is you can still access it as a disk, but you have to really recognize that it's not a disk if you want to get your money's worth in the best possible way. So that's sort of the phase that we're in right now. The third phase, which is sort of coming, is recognizing that it's the high end of flash really merges well with memory, and really what you need to think about is a trade-off between kind of DRAM and flash, or DRAM, other media, and flash. So the flash world, for example, you could think of it as is it intended to really replace the high end of disk? Is it a disk replacement kind of technology, or is it a form of efficient memory where you can create hierarchies with DRAM and flash? So that's the phase that we're moving into, and technologies that follow flash really fit into that world. You can get there with flash also, but that's kind of the world that we're moving into. So what we're going to talk about today in the first half of the talk is the second bucket, which is how do we optimize for flash in a way that's unique to it and goes kind of beyond the disk model. Second half will be about the other topic. So we've talked a lot about how the software is the limiter, and how optimizing the software can help. So, we've built software in this area. We've tuned existing software also. We've tuned software, we've contributed to software, we write software, all in an attempt to help applications connect with the devices in more effective ways. So one piece of software that we have released, we've talked about it before, but it's now, generally available for people to deploy, is an NVM optimized file system. So essentially what we're recognizing is people like to manage this stuff the way they manage storage. They don't really want to know that they're managing flash. People like files. Files are easy to deal with. Files are easy to manage with. And so by creating a stack that helps people manage exactly the same way they did before, but recognizing that flash is a different kind of media, memory is a different kind of media, you can actually create file system technologies that are manage exactly the way they are before, but they perform and they're more efficient when they're running on flash.
So is that available? I assume it's on Linux, right?
It is on Linux, yes.
Is it open source? Is it closed source? How is it available?
It's currently a proprietary file system. Fusion.io recognizes the value in creating open source, and we're now helping to educate our new parent company, SanDisk, on the value of open source. So we see it as a strategic direction, and I can't say much more than that, but if you do a Linux file system, what license do you use for a Linux file system? That's really the question we're asking internally.
Yeah. And the Linux folks have been resistant to non-open source, especially file systems.
They seem to be sort of religious about that.
Yeah, exactly. And so is it the user space or kernel mode? Is it free? Is it free?
So it comes with our devices.
Okay.
Right now we look
It's free when you buy a, yeah, okay.
But the answer to the next question will make that clear. And it only talks to your devices, right?
no, it talks to a variety of devices, but it's only enhanced for our device because it needs those primitives.
And this is actually not something that was commonly known in the past, which is, it has the ability to talk to a variety of devices. We are currently only providing it with our devices.
The file system itself works on any storage platform. It's a file system.
Right, but it's not. But it's optimized to the Fusion.io controller, not to NVMe or some other standard. Yeah.
So, so to answer your question, Linux has a standard place where file systems plug in. We plug in there. So anything you do with a normal file system, you can do.
But I am not running Fuse.
Oh God, no. Okay. Yeah. Oh God, no. No. Yeah. No.
Exactly the response we were looking for.
Okay. All right.
Oh God, no. Yeah.
Yes.
Yeah, and so it's free, but it's only worth having if you have with the device. But it's only really worth having if you have the device. So who cares?
It's actually a really fast file system regardless, but it doesn't give you the kinds of optimizations that make it noteworthy unless you've got an IO memory card underneath.
Allow me to say what you can't. It without the Fusion.io card behind it, it is yet another file system, and it's not like we have any shortage of those.
And I think that's actually a really good point, which is there are a lot of file systems. So, why introduce another one? And frankly, in my opinion, the only reason to introduce another one is if there's something so fundamentally different in either the current use of the flash or in things that come after flash, that, retrofitting an existing file system, that was written, 2 decades ago, may not be the wise thing to do.
That's why we called it NVM FS and not
It's not Flash FS for a
yet
reason.
another file system. That was an option too.
But actually, it's very important. There's a reason it's not called Flash FS, or the word flash does not appear. The word non-volatile memory very intentionally appears.
Just because you want to be prepared for STT.
We want to make something that's hard to say. Try saying NVM FS 5 times fast.
So NVM is non-volatile memory then?
Non-volatile memory, flash plus other.
It's one of our bits of jargon, yeah.
All these TLAs.
Yeah, because networking doesn't have enough of those.
No, most of the networking ones have 4 letters.
Inversions.
Did you guys intentionally have the storage guys and the networking guys? You're the spy.
It's peace. It's, yeah.
The table slows us down.
Yeah. Okay, sounds good. So before we get into the Before we get into the technology, just I'm not going to read through all of these, but wanted to make it very clear, which things are released, which things are not. These are the things that are released. We'll be talking about. We already talked about the file system. The file system has some notable capabilities within it, which all got released with it. There's a number of database, specifically MySQL variants that have been released for a while, or recently, depending on which one you look at, but all of them are out, and they work with the file system, and we'll talk about some of the data that comes.
Its name, so that's really very unique. And also, it's worth mentioning that this is, as we said, when you get this optimization stack, it starts to become the bottleneck is in the application. So working with the MySQL team and giving them a little bit of code to start with, we were able to have them modify the MySQL code base to use this new I/O path. That's why we're seeing an emphasis on MySQL, not because it's specific to MySQL.
It's not specific to MySQL, it's generic database stuff. Now, it's actually worth noting.
It's a lot harder for you guys to patch it into Oracle.
SQL Server, Microsoft gets all upset. Exactly. Try to modify SQL.
So it's part of this is that, applications change slowly, right? And the open source world changes much faster. The principles are the same. So if something works in an open source database using a common principle, it has some application.
Oracle and Microsoft are waiting for T10 to get their fat asses off of atomic rights.
And we're driving that.
We've actually, I have a slide on that later. Okay. Yeah. So there was something else I was going to say. I don't remember. Oh yes, what I wanted to say is, so one of the things that it's actually probably worth noting is that when these applications do optimizations, they're not using an API of ours. They're using variants of classic. Basically, they're using POSIX. So the stuff will run on any file system, but to Dan's point, some file systems are not as tuned for flash operations and others. So
well, at this point, Atomic Write is a proprietary API.
No, not here. No.
We'll give you the link.
We'll give you the link. There's no proprietary APIs being invoked in any of these apps. They all use POSIX calls.
Previous slide, the SNEAL link. It's on the slide.
Yeah, we have a slide, but we'll share it with you. But suffice it to say, these are all POSIX calls that are being used. It'll run on any file system, but some of the operations are much faster on NVM FS, and some of them are simply not available on other file systems.
So we're not talking about the Fusion IO Atomic Write. We're talking about NVM FS.
No, we're talking about write with an iOctal prior to it.
We're talking about implementation of the standard Atomic Writes API.
Last time I checked, there was no standard Atomic Writes API. Please inform me of how I'm ignorant in this.
So let me maybe separate this into two things. So first of all, standards are at various levels. The T10 standard for Atomic Writes is actually approved and has been approved for about, I want to say, more than 6 months. It's okay. So that's okay. That's been approved for a while. I have a link to it somewhere in this talk, so you can have it. Separately,
somebody else to support it, but. Yeah, a standard that only you support is different than a proprietary API. Granted.
And as per standards committees, it took a while. There are several others in the proposals in the works as well. But
I'm the one who used the term "get them off their fat asses" because I thought they hadn't approved it yet.
I'm the one who's being recorded, so we'll leave it at that. So okay, so this gives you kind of where to get it. If you have any more info, please let us know and we can help you. But this at least will give you a summary. So what is NVM FS? Very specifically, Flash and other. POSIX compliant, lives in the kernel, plugs into the VFS, vnode infrastructure the same way any other file system does. It will do anything, but our focus has been on what we would call, data-intensive, database-like workload. So we are really not necessarily looking to support your home directory or, things like that. It'll do that, but that's not our focus area.
Home directory ever.
Yeah. So what do we focus on doing really, really well? Things that databases and applications like it which is data-intensive workloads, direct I/O, being as close to the performance of the underlying device as possible. I have a chart on that. So really, what we want in the ideal scenario is you get your file namespace and your manageability, but you get the performance you would have gotten if you did raw I/O to a LUN or something like that. Databases like to pre-allocate files. So an interesting thing, which is the concept of file system aging. So file systems age, and what that means is that over time, as they start creating, deleting things, allocating, deallocating things, they get fragmented. Now, that's a normal thing in most file systems. Now, the interesting thing is that SSDs make everything faster, including fragmentation. So fragmentation is a result of data traffic. So if your SSD can do your data traffic 10 times faster, your file system ages 10 times faster. So one of the and this is, and the faster your SSD, the faster you're aging. So one of the things about NVM FS is that it has no aging in the capacity sense and very, very minimal aging in any other sense. And that is one of the things that, is about being flash aware, is things that, get worse over time don't get worse here. It exports some of the capabilities of the underlying devices, as we've been talking about, and it's designed for flash and things that come after flash. This is a multicolored picture of NVM FS. Short version is it plugs in the same place as everything else. It does a lot less capabilities when it's running on top of a flash translation layer that it can leverage some of the capabilities of. And, and basically, there's a lot of things that are very disk-oriented that really don't get done in NVM FS. NVM FS is much thinner, much lower in code count, than other file systems.
Well, the important thing to highlight here is in a standard file system, this is true Linux and non-Linux, there's a whole set of functionality that's happening at the file system level that's done again within the flash translation layer. And that duplication of logic creates its own bottleneck in that I/O path. So part of what we did in NVM FS is strip out those things that don't need to be done because they're going to be done in the underlying files.
So rather than journaling metadata updates, you're doing atomic writes for them?
Yeah, absolutely. We don't have a journal for exactly that reason. So, okay, this is the one. So this is a chart of performance of NVM FS. In first two bars are read and write for one I/O drive. The second and third and fourth bars are read and writes for 8 I/O drives. And in both cases, what you really want to see is the black line is what the devices can do. So you can't really do better than the devices. What you want is to be as close to the devices as possible all the time. And so the basic idea is that, whether it's a read or a write, the green bar, which is the NVM FS bar, is pretty much, nearly indistinguishable from the performance of the device. And that's true even when you have 8 high-performance devices ganged together. So, and whereas, in this case for XFS, which is frequently the fastest of the available file systems out there, it varies. Sometimes it depends on the read and the write. Sometimes it depends on how many devices there are. Varies, but the performance doesn't match the raw device. Matching the raw device is what we want to be at. So you can imagine that the faster the flash gets, the bigger this gap grows. And the acceleration varies. Sometimes it's 20% faster if you're doing something simple. Sometimes it's as much as 5x faster. So we've talked a lot about atomic writes, so I'm not going to talk about it in much depth, partly because we're running out of time. Atomic writes has been around for a while. We've demoed it, we've talked about it. So it's also been released for a while. Probably the most important things to note is, using atomic writes at an application level, you can get a pretty nice improvement in throughput. It has been standardized. So there are various proposals in T10 right now. The primary atomic writes proposal was standardized. There are other outstanding proposals like scattered writes and gathered reads and things like that are still going through.
And you guys can do those things with your own, with the Fusion APIs.
We can, but we are also, there isn't anything that we are doing with the Fusion APIs that we haven't really put into a standards body. There's also the SNIA non-volatile memory programming twig, which has a programming guideline for both I/O-oriented and memory-oriented non-volatile memories.
Things like scatter-gather haven't been approved yet. You've put them into the standards body, but they haven't come back out again.
No, they have not, yes. The main point I wanted to make is that the atomic writes that we normally talk about is actually only the approved one. The others are, not the one. So when people talk about MySQL using atomic writes, they mean only the one that's been approved. Not because it's approved, but because that was the one that was actually used.
For those of you dealing with networking stuff, does the atomic writes, do you understand the optimization there, what we've accomplished?
Not exactly.
Yeah, maybe the couple sentence of atomic. What is atomic writes?
So basically, when you're talking about storage devices, Storage devices, if you write to them in something that's bigger than a sector and the device fails, the device is not expected to have an all or nothing characteristic. They could have written all of it, half of it, any combination thereof. And so because of this, applications like databases and file systems typically either write ahead in a journal or they write it twice in some way, and they make sure that if something crashes and the write gets torn, it's called a torn write, then they can find a good copy somewhere. So what that means is that the flash device gets effectively twice as much writing to it because they can trust update in place once. Flash devices internally are log structured anyway, so it's actually a fairly straightforward operation inside a flash device to provide very high performance, all or nothing semantics for writes. That's what we do in atomic write.
So let me guess, you're writing to a different place, and when you're done writing, you change the pointer.
Which is what you have to do for Flash always. So atomic writes is kind of so natural for SSDs. It's annoyed me it's taken this long to get the standard done, because you say begin transaction, you write all the new data to the new location in Flash, and then you only update the logical to physical pointer table when you get the end transaction. So it's just defining the semantics for begin and end that had to be added, because all of the rest of it is just how Flash has to work.
And then, as I said, the bottleneck moves then to the applications that are doing the double writing. And so what we did with MySQL code was go and eliminate that double buffering, so that when it recognizes, and it actually does detect when you fire off MySQL, it recognizes that it's got an atomic writes aware and capable file system, and it no longer does the double writing.
So you removed half of the writing code.
Yes. So what that, and the interesting thing about Flash is that, when you write to Flash, that is actually the most expensive and difficult operation for Flash. It causes erases later, it causes garbage collection causes, additional load that then causes, performance to change and things like that. So the less you write.
It causes anger, and anger causes hate.
Much happier.
You must unlearn what you've learned, Howard.
In this metaphor, is the T10 the empire, Howard?
No, the T10 is
Let's not go there.
Mace Wangu.
Yeah. So that's the basic idea of atomic writes. It's
Just to be the commercial guy to put the emphasis on this is shipping today, so you can actually run MySQL in production on NVM FS on an IO memory card.
And this is basically the standard MySQL builds coming from the standard vendors, not like a special build for this stuff or anything like that. The standard one. Exactly, that's the point. And it's auto-discovered, so if they know it's there, they will basically turn off the alternate technique. If it's not there, they'll turn on the alternate technique. So, perfect. So that was atomic writes. So what we demoed last year and released earlier this year is what we call NVM compression, which is complementary to atomic writes but doesn't require it. What this really says is, so if you think about like compression, right? Compression is another case where applications do something that devices do natively anyway, very, very efficiently and at super high speeds. Whenever you compress data, what happens is that data that comes in changes into a size you can't predict when it came in, which means it may or may not fit in the place it used to be, which means you have to find a new place for it, and now you've got a hole that may or may not fit something else, and now you have to, garbage collect all of that and gather all of that up and so forth. And so whenever applications compress data, they end up doing a rearrangement exercise that, is usually fairly complicated. So what we do with NVM compression, and again, this happens through existing POSIX APIs, in this particular case, fallocate, is you can write your file as if it was compressed, just uncompressed. Just put your data wherever you put it and leave a hole in the space you didn't write. And the device, and with the help of the file system, will clean up those holes and make sure that they don't become actual space on disk.
Just to answer the anticipated question, it's not about, that's about the management of the compressed data. It's not about the compression algorithm itself.
Yes.
So NVM compression is not doing compression in Flash. NVM compression is dealing with compressed data.
It's dealing with the patterns caused by compressed data. So the application can compress however it wants, using any algorithm it wants. It doesn't have to use the same algorithm the second time around.
But you're doing blank space detection.
We're doing blank space detection and
tight packing instead of keeping it to 512 byte blocks.
Or packing it in multiples of 512 instead of multiples of like 16K or something like that. Yeah. So effectively, think about it, packing it at very high speeds is what flash devices do for a living. So therefore, essentially now any application can get that speed of packing without implementing it themselves, but they can compress the way they want.
Over what kind of data realm are you doing the packing? Because, some of the storage systems that do compression badly, they'll take 8 or 16 sectors and compress it down to whatever smaller number of sectors it comes down to. But of course, if 8 goes down to 3.5, you're still wasting a half. And so the larger the realm that you type pack across, the more efficient it's going to be.
So basically, we don't.
The answer is the whole file system.
Well, actually, when you mean the whole file, do you mean the whole file system at a time, or do you mean on an I/O?
You're talking about compressing the files in the file system, right?
Well, if you're stuck in the disk paradigm, everything has to break down into 512 bytes. Because you can't do anything smaller than that. And the way these systems work is they take n by 512 bytes and compress it, and they end up with y by 512 bytes. But n is a fixed number, and y is a variable number, but there's always some large fraction of the last sector of y that's still free space. And so, we've gone from, okay, we have this much free space to this much less free space, but we still have some waste.
Directly answered on the next slide.
To directly answer it, we compress only to multiples of 512, and there's a reason for that. The reason is flash specific, which is, if can you compress to less than 512? Absolutely. That would cause you to have to change the ECC in your devices, probably. And so what this gets you is, another way to think about it is, what is the size at which you compress? That is whatever the application cares about. In this particular case, it happens to be 16K because that is their block size. But that's not determined by us. That's whatever the application chooses, it's fine. What we can manage very effectively.
So it's based on the write I/O size?
It's based on their block size. Like all databases have a block size. Database block size. Write page size at the database level. So going back to your question about can you make variable bytes, it's possible, but it requires far more impact to the device. It's not as much trouble as it's worth, exactly. It's more trouble than it's worth. So what we get is essentially, we can get to anything that's at sector granularity. That means that obviously, 2x you can get very, very cleanly. If your application supports more, you can get as much as, you can compress down to a sector if you want. That gets you money. Exactly. So effectively, this is kind of what we do, which is the application takes whatever size it has, it compresses, it writes in whatever is the rounded up 512 that it has, leaves a hole for the rest of it. We only use the 512. We clean up the holes, and then, and the capacity just naturally expands. So one thing to kind of note about this is that, like NVM FS, for example, and again, this can work with any file system, but NVM FS, for example, doesn't have a static link between the capacity it exposes and its physical. So it knows when it's running out of physical capacity, but if you didn't use up the physical capacity, you can happily put more files. You don't have to resize the file system, you don't have to grow it, shrink it, anything else.
Okay, so this is a function of the Fusion FTL?
So the app is doing the compressing and leaving the holes.
Right, the packing.
The packing is a function of the FTL, yes, precisely. The file system is the plumbing in between. So
actually, go back for just a second. I want to give a little bit of context to this. So again, NVM compression in this particular instance is MySQL specific.
Yes.
Because what occurred was, as part of the development process that Nish's team was going through, they looked at the capabilities Flash had and the types of problems it could solve, and discovered through that process the inefficiencies in the MySQL compression logic, because it's there in open source, and developed the initial code to use this sort of an approach.
That makes more sense.
And now the MySQL guys have embraced it and incorporated it into their distributions. It's a little bit behind the development curve from Atomic Write, so MariaDB has it out in its supported version now. Oracle's coming with it shortly, and Percona is following the Oracle path. But this particular implementation is MySQL specific, and it is a representation of what we expect to happen over time. which is the capabilities of flash when exposed as a memory device instead of a spinning disk I/O, introduce the ability to do all sorts of efficiencies across multiple storage management problems in the software space. And this is just an example.
And I think maybe one way to kind of, I'm sorry, you had a question. Go ahead.
You're using a POSIX call.
Yes.
Correct.
This is not MySQL specific or anything.
Well,
Anyone could use it if they get
compression
smart.
Algorithms were, but
Yeah,
the architecture is not.
So like one way to think about it might be that how does this integrate into MySQL, right? And that'll tell you whether it can integrate into other things. So the way it integrates is it integrates at the lowest level of the database, where the database is about to write out effectively a 16 kilobyte page, and says, okay, now I'm going to compress it. And, and after I compress it, I'm going to write out whatever size it was, it compresses into, and I'm going to leave a hole in the rest of it. So given that it actually happens at the lowest end of the database, you can imagine almost any other app above. As long as it had a fixed block size, and as long as it had something in its metadata header that would help it identify that this thing was compressed. Coming back, it doesn't even need to know what size it is. It can just read the whole part, and the part that's populated will show up. So in that sense, it's the implementation is very MySQL specific, but the way it's done is not really tied to the database.
The way compression was managed in MySQL code previously, they had a complex set of kind of link and block management logic that tried to use this unused space and then had links to more blocks, and then when it overflowed, they'd have to redo the entire tree from
You effectively end up with something as complex as an FTL.
right. So it was doing all that storage management logic up in the application layer. To just manage
It's basically trying to manage its own scattered file system.
It's its own I/O stack, basically. And the truth of the matter is that those are the types of implementation problems that are across software stacks of all types that these kinds of optimizations now offer ways to work around that weren't available.
It's a solution to the mismatch between fixed page sizes and compression.
Between memory and disk. There's no longer a memory disk.
Yes. Yeah, packing of data into multiples of sectors was never a natural thing. It's something people learned to do because that's what storage offered.
Storage folks do all sorts of unnatural acts.
Yes.
That coming from a storage guy.
Essentially, it's a TPCC-like workload, which means we're not allowed to say it's TPCC. And right. Okay. So essentially, what this really shows is the gray one is traditional MySQL compression that tried to do all the data rearranging. The top one is, I'm actually not sure which one is the uncompressed and which one is the NVM compression. They are about the same.
The top one is uncompressed, which is, in other words, the most you could expect in terms of compression performance, right? And then the red line right underneath it is with using NVM.
So there's still a performance penalty for compression, but it's shrunk substantially.
Someone has to burn CPU cycles compressing it. Come on.
But here is an interesting thing. Yeah, but here's an interesting thing which is that flash devices perform better when you write less to them. So if you are in a situation where you're using more CPU at the device, but at the host, but the device is running faster, we've actually seen cases where if you compress efficiently, the compressed performance can be better than the uncompressed because the device is faster. And so that's why I couldn't tell. Yes. That's why I couldn't tell which line it was, because we've had many runs where the compressed actually outperformed the uncompressed, and with good reason. So this one is LinkBench. So LinkBench is a workload that simulates Facebook social graph. It's an open source benchmark written by Facebook. And what it shows, row compression is the standard MySQL compression. Uncompressed is uncompressed. And page compression is really NVM compression. So you can see that it's basically, very, very close to uncompressed, even on this workload, which is a very different workload than the TPC-C workload. How do the latencies do? The latencies of NVM compression are very close to those of uncompressed. All the tall bars in this case are we have a palette problem. So all the tall bars in this case, all the bad ones are the row compression. All the small red bars are the uncompressed. Yeah. So essentially, it's sort of interesting because this, if you think about it, is another good example of if you write less to the device, it does less garbage collection, its latencies improve. And as a result, you can actually get it to behave better, and your database runs better because it is sensitive to the latencies of the I/O device.
It'd be interesting to graph and show consistency of latency, latency over time of the benchmark.
Right. This is actually 99% latency, so it speaks to consistency at some level, right? This is outlier latencies. What we have noticed over time is, over time, the performance delta between uncompressed and compressed tends to get lower. And so when we see compressed outperforming uncompressed, it's over time, because the effects of writing more build up over time. So over time,
and then you get into more frequent garbage collection cycles.
And you go into more frequent garbage collection. So this is actually a very interesting thing. Usually, flash benchmarks get worse over time. The only time that flash stuff gets better over time is when you write less to it. So the NVM compression performance improves over time.
So when you say time, what's your frequency of? You're talking about when you're measuring?
Years, decades.
Well, I mean, what's a reasonable time frame?
The time necessary to write more than 1.5 times the available capacity of the device.
Yes, and how long that takes depends on your application, right? It depends on your application. In something like a TPCC benchmark, if you configure it, it takes typically about a day or 2 days to get fully into the garbage collection zone, because even TPCC doesn't write fast enough. So if you really just wrote a benchmark that just hammered the device, you could overwrite it in under an hour. But if you're writing a real app, it takes typically about 1 or 2 days before it really gets into sustained mode.
Are the games you guys play in the arrays to sort of stretch out how this would work over the number of devices you have, or is that a linear sort of relationship, or is that different?
Well, so I don't know how it's done in
Yeah,
Flash,
it varies depending on the architecture of the flash controller in the SSD. But what causes the problem to happen, so if you buy a 400 gigabyte enterprise SSD, it's got 512 to 600 gigabytes of actual flash. Once every page of that actual flash is dirty, then you start suffering the problem. And so it's very much a how much data you've written. Now, better SSDs so most SSDs have multi-core ARM processors in the controller. Right? Cheap SSDs have fewer cores. Better SSDs have more cores. You write the firmware so that it starts doing garbage collection in the background before it hits all the way full, and the degree of impact becomes smaller. But a fresh out of the box SSD where you never have to wait for a page, right? So you know that flash pages are like Etch-a-Sketches. You have to erase the whole thing. As long as there's a fully erased page to write data to, performance is relatively consistent. As soon as the rate at which you're writing data exceeds the rate at which you're doing garbage collection in the background, you start seeing that the rate at which you can write data slows down because you have to wait for a page to be erased before you can write to it.
So, I mean, there is a correlation where if you're snapping in additional capacity, you're delaying this process definitely.
An all-flash array is responsible for doing wear leveling across all of the SSDs that it contains, as well as the controller in each SSD, wear leveling across the flash within that SSD.
So within something like InfiniFlash, where you have half a petabyte, you've got a lot of storage to aggregate that problem over.
Well, and InfiniFlash has the other advantage of it not having a standard disk interface between I'm going to call those cards SSDs, but there's a flash card, and the controller on the flash card isn't a SATA or SAS interface to the next step up controller. The problem is SAS and SATA don't have a leave me alone for 400 milliseconds because I'm doing garbage collection message. If you're building your own system from scratch, then each of the individual modules can apply back pressure, which just tells the wear leveling algorithm in the system controller writes that come in while he's busy doing garbage collection should go to one of the other guys. And well, reactive, you're always trying to spread the load out. You start off trying to spread the load out evenly. But you can make it reactive and make your latency much more consistent. And this is kind of the next.
So essentially what happens is that, if you have a very, very large capacity, and you're writing little enough, you may never run into a situation, but it depends.
Background garbage collection, as long as the background garbage collection is as fast as the write rate, then you're cool.
But what happens is that if you're writing at any level of intensity, and you're right, then eventually you are going to fill up the device because the device cannot overwrite. Depends on how intense it is and how big the device is. For something that is, like say 1 to 2 terabytes and you're running a normal single server, transactional workload, it takes about 1 to 2 days to, get yourself into the situation. When you get into the situation, the problem is exactly, as Howard said, which is now you've got all these erase blocks that are partially filled. Say hypothetically they're 70% filled, right? Which means that now 2/3 of this thing is full of useful data. In order for me to claim that 1/3 of space, I have to move the 2/3. So for every 1 unit of data I write, I have to read 2 units and write 2 units that I didn't put in before. So which means that effectively my workload for the same application activity has gone up by 5x. And most devices have a limited amount of resources to manage this. So unless you have enough resources, it's going to show up as some intentional or unintentional back pressure, latency, throughput, which is why reducing the number of writes goes a long way towards just keeping everything behaved.
In the storage world, the cardinal sin was always moving the heads. It's like, don't do a random I/O, you'll have to move the heads. That adds 5 milliseconds latency. With flash, the cardinal sin is writing. You want to, everything you do is to minimize the amount you write.
Don't ever write to the database.
Excuse me? Yeah. Unfortunately, we have those darn users who keep trying to write to the database. I know. Yeah, everybody in IT knows the real problem is actually the users. Yeah. Of course, if it wasn't for them, we'd be unemployed as well.
Uncompressed clearly writes a lot. NVM compression clearly writes a lot less. Again, very data dependent. This is one experiment. It doesn't need. Oddly enough, existing compression writes more. And really the key thing there is that if your space management gets so complicated, you could actually end up writing more. Just because you have to clean up the mess that you've created by rearranging your data all over the place. So you may think straightforwardly compression should cause you to write less. It's not at all. Depends entirely on how you did it. Sorry?
We call that retransmissions.
Yes, it's effectively it's a retransmission. Yes, it's a retransmission of sorts.
But we're storage, and we don't do retransmissions.
Let's not lose the fact that in the flash storage space, this has direct customer value and monetary impact because it extends the life of the flash device as well as increasing latency. So they get more out of their cards. Right?
Higher density, lower cost flash, more usable in environments it couldn't be better.
Some of these problems by just throwing more flash capacity at it, and so it's got a direct cost.
Correct.
If you try and solve it by further over provisioning.
Yeah. So oddly enough, I was thinking about this retransmission. We do retransmissions. It's just that we get the data from the other guy and send it back to him. We do read and a write when we rearrange stuff. So which would be the network equivalent of, you've got my packet, I want to send it back to you, give it back to me so that I can send it back to you, kind of thing.
The compression is more like encapsulating.
So, yeah.
Eventually, your payload becomes so small that it's not relevant anymore because your payload is just the header of the last one that you tried to stuff in.
So this is VXLAN over IPv6 over IPv4 over BPPoE over MPLS.
Over token range.
Yeah.
This essentially shows that compression runs at lower wattage than the uncompressed. It runs cooler than the uncompressed. The actual card is running cooler. So saves power. Again, the benefits of not writing as much. And I think since we're out of time, I'm going to skip the summary. I think we've talked a lot about it. But essentially, what it comes down to is it works really, really well. And the less you write to the drive, you get unexpected benefits.